Thanks. I'll begin with a word of prayer. Dearly Father, we thank you for this day. Thank you for these students. Just pray to be with us. Help us again, Lord, to glorify you. We thank you that you won the battle already when you came to earth and died for our sins, Lord. We just thank you for being the awesome God that you are, Lord, each and every day. In the name I pray, Lord Jesus. Amen. So I want to just spend a couple minutes. I don't remember if I did with you guys or not yet, but I have notes that I've written. Well, I've told you guys before about how we can look at the Taylor expansion as a way to understand how functions behave, right? And so ignoring weird examples like that bump function I showed you, which is smooth but not analytic, right? That's a weird function. Most functions aren't like that. Most functions are analytic. And most functions, we come across in applications at least, the Taylor series is a good tool to analyze the behavior of the function, right? So, for example, we can think about the Taylor series as a way to understand the second derivative test in Calculus 1, for one thing. Here's another example. The relativistic energy of a free particle is given by this. This is one of the things that is derived from Einstein's theory of special relativity. So what you have here is the rest mass times c squared divided by 1 minus v squared over c squared. If you look at this function, it has domain between minus c and c, right? As long as the velocity is between plus or minus the speed of light, which is c, this function's well defined. If your speed of light is larger in magnitude than c, then this becomes imaginary and things require more imagination. Like we don't know. Anyway, so if you want to expand this as a power series about v, you could do that. So like, for example, dE dV is this divided by 1 minus v squared divided by c squared to the 3/2 power. So I'm basically doing like your section 12.6 homeworks, taking some derivatives to calculate the power series here. And so then v equals 0 is a critical number, the energy. Okay, after a little more calculation, you can show the fourth order Taylor polynomial and velocity v for the energy E is the following. So like the 0th term is m naught c squared, then you have plus 1/2 m naught v squared, and then plus 3 m naught divided by 8c squared times v to the 4th. So this is what the relativistic energy is expanded as a power series in the velocity. Now, you've probably heard people talk about this term a fair amount, right? M naught c squared, or mc squared as it's usually referred to. This is what Einstein found, right? And it's surprising because once you find this power series expansion, if you studied physics before, you know what this is already. What's this? Well, I mean, this is just ordinary classical kinetic energy, 1/2 mv squared, right? So it's very weird to find something you have a good explanation for. You already know what this is, right? And then there's this lower order thing sitting over here that's way bigger than that. It's very striking, isn't it? And of course, that's where we get nuclear energy and peace in our times. So anyway, this is of course the nuclear term, the so-called rest energy. Anyway, here's a graph. The classical kinetic energy is unbounded, right? So for a given mass, you can have 1/2 mv squared as big as you like because v doesn't, I mean, classically speaking, there's no reason you can't go 20 times the speed of light. Nothing in Galilean physics and Galilean relativity forbids faster than the speed of light, whatever. So the green would just keep going, right? But in Einstein's theory, the cosmic speed limit is plus or minus the speed of light, which here I've graphed as 1. And so like the red is the relativistic kinetic energy. If you can use your imagination, you can see that that's something like, well, I guess it's hard to see it, but that's something like v times sinh, or x times, well, anyway, I'll shut up about what that is, that shape. Now, you can ask, excuse me, how far off are you, right? How far off are you by using, like thinking of energy classically versus relativistically? How much energy are you off by? And that's a subtle question. I'll look at an example which is a little bit less subtle, all right? So we can kind of appreciate. This, of course, is the error. This is the remember the Lagrange's form of the remainder, basically. It's written in a kind of funny way. If you put b equals to x and a equals to 0, then you've got what the book wrote for Lagrange's form of the remainder in 12.6, because he only looks at Maclaurin series in 12.6, right? So again, if you put b equals to x, and if you put a equals to 0, then that gives you the formula which we had in section 12.6. This generalizes that for an interval which, say, goes from a to b, right? And you think of v as the variable, then you get the absolute value of, anyway, this is the Lagrange's form of the remainder. So that pretty much pins down the size of the error in a given, and there's the proof of it, which I will post a link to. I don't know if I've posted this in course content or not, you guys, and I keep forgetting to look when I'm away from you, but I will try my hardest today. I've got a faculty meeting coming up, so that means I've got some time to look at things. Oh, wait a minute. Don't tell your dad. Let's see here. So, sorry. I will be paying attention, of course, as I always pay attention in faculty meetings, especially when we're talking about things that aren't about our department. Let's see here. Anyway, I digress. Maybe now when I show you this picture, it'll make more sense. So what I'm looking at in this case is a fifth order polynomial, 6x to the fifth. Who cares the formula? It's a fifth order polynomial, right? And what I'm doing is I'm approximating that with what? With a quadratic, I think. So I calculate T2, or as your book would call it, P2. T2 of x is f of 2, f prime 2 of x, plus f prime prime of 2 divided by 2, x squared. Why don't I have, if I'm plugging in 2, I should have like x minus 2 here. Yeah? Yeah. Yeah. Maybe I mean 0, actually. Yeah. I do believe I meant to put 0 here. There's a typo. Sorry about that. Obviously, this is a, where is it? I'm losing my eyes are blurry. Well, this here is this is a Maclaurin. I mean, this is just this is 2 minus 30x squared is actually what I'm using to approximate f of x, right? And so if you look at the third derivative, you've got this, all right? Why do I look at the fourth derivative? Well, what's that? No, not that this time. What I want to do is Lagrange's formula for the remainder. I'm trying to put a bound on the error here, right? So you guys had some problems in the homework where they're like, the third derivative or the nth derivative is bounded by 3. Well, yay, that fell from the sky. Like, what if it doesn't fall from the sky? How do you bound the error in a particular derivative of the function? Well, one move I have, a go-to move I have, is I look at the next derivative. So like if I want to put a bound on the third derivative, I look at the fourth derivative, and what does that tell me? Well, the fourth derivative is positive, right? So what's that mean? That means the third derivative is an increasing function on the interval. So all I got to do is take the value it gets to at the end of the interval, and that gives me its largest value. So if I know that the third derivative is increasing, I can pick its value at the right endpoint as a bound. That's the idea. So basically just calculus of graphing applied to derivatives. So that's my logic here. That's why I get that f prime prime of x, well, that's an upper bound, but a lower bound would be f prime prime of minus 1. So basically what I get here is this. So I get a bound of minus 92.4 less than the third derivative less than minus 20.4. So if the epsilon value of x is within 0.1, then the third derivative is less than 92.4. So that gives me what I need in order to use Lagrange's formula, the error estimate, which derives from Lagrange's formula for the remainder, right? Which is based on the existence of some point where the whole error term is bound up in the next derivative term past the one we use in the Taylor approximation. It's equation 12.5 or I want to say 12.5.4. That seems wrong. 12.6.4 must be. I think it's on page 599 of your book. But anyway, I hope you understand what I'm talking about without regard to specific book numbers at the moment. Anyway, so I find the bound on the error is 0.123, and I actually took a second to make a picture of it. So like I forget which one it is. Oh, here it is. The red curve is the actual function. The green curve is the approximate, and the gray band shows the hypothetical 0.123 error. As you can see, if I worked harder, I think I could get a better. I mean, obviously my error estimate is very generous, like too generous. So I think it's pretty clear you could do a lot better, right? So anyway, I don't much care about getting the best approximate. I mean, if I was doing a course in numerical methods, if this was all we were doing, I wouldn't be happy because I'd be like, well, I can do better than that, right? But we're just looking as a starting point here, something reliable, not necessarily. We're looking for something reliable to explain the error, not necessarily something optimal, okay? I may have showed you these pictures before, but I hope you now better understand what they mean since we've been working with series for a little while. So here's like a more global picture of that. You know, this is the quintic, the fifth order polynomial, and here's the approximate of it through the origin, well, through 0, the quadratic. As you can see, it follows it quite a ways. And it follows it precisely as the Lagrange's formula for the remainder dictates, yeah? So, I mean, the point of this part of the course, right, is to teach you Taylor series and how to approximate functions using Taylor series, right? Also how to calculate with Taylor series, but as a first order of like concept, how to approximate with Taylor polynomials is the first thing, right? So in order to make that a valid thing for you, you need to have some measure of how far off you are, right? That's why this discussion is important, because it actually puts teeth into like how good approximation it is, which is important, right? If you're working for some employer and you want to use a Taylor polynomial to approximate some function in your work, well, you know, you want to be careful. So this is how. Here's another one. This is sine x. And here's a similar picture. I work out the error bound in sine to be whatever it is. And here's a picture of the, so you read through here for the details, but basically I derive the error being that gray band. And here's the function is the red one, and the Taylor polynomial is the green one. T2 actually I use. So here's T2. The gray band shows the hypothetical error allowed by Lagrange's remainder on the interval -1 to 1. So I guess I could assign homework problems like this. Use Mathematica to create a pictorial representation of the error in your. Have I been talking that long? Oh, no, I better get on with it. Let's see here. So I do sine again. I think this time I kind of go a different way. I say, suppose you want the error to be less than 0.1. Within 0.01. Why do I have 0.1 here? That may be a typo. I don't know. I think what this shows you is that sine x is equal to x within a 0.001 between plus or minus 0.42 radians. I think that may be a typo right here. I think that may be supposed to be 0.001 right there. Anyway, what is 0.42 radians? Yeah, I don't know either, right? But if you convert it to degrees, what do you got? 24 degrees, I say, thankfully here. Right? So it's about 24 degrees. So that's where that part of where that you can approximate sine of x with x up to about like a percent, where between plus or minus 20 degrees. So here's the math of that. Here is calculation of the square root of 0.403 using second order Taylor polynomial. Oh, anyway, there's an approximation for the square root. This is what I want to show you. Let me keep going on here. This is the example I wanted to spend just a little bit of time talking to you because I think this is an interesting application. And so if you look at Newton's general gravity, right? The inverse square law, gmm over r squared. This is Newton's formula for the universal gravitation law. In particular, this is the force a mass big M pulls on a mass little m. If their centers of mass are distance r squared apart, it's attractive, it pulls towards the center, right? So just to draw a picture of this, Goodness gracious. So here's m. Here's little m out here. This distance between their centers of mass all the way is known as r, right? So that is made of two things. First of all, the radius from the center of the Earth, and then what we call the altitude. So little r is equal to the radius from the center of Earth plus the altitude, right? Now, of course, the radius from the center of Earth is pretty much fixed, right? Unless we're, even Mount Everest, it's not much different, right? Radius from the center of Earth is something like, I don't know, 6,000 kilometers or something. It's big relative to the size of things on Earth, right? If you zoom out from Earth, it looks like what? It doesn't look like, it doesn't have a jagged edge, right? You can't see the mountains if you're in space, right? So anyway, if we replace this r with r plus h, then we can look at the force of gravity as a force of altitude, according to this formula, right? If you differentiate that, you get this. And if you take a second derivative, you can see it's less than 0, so that means f prime is a decreasing function. That allows me to put a bound on the first derivative. In particular, f prime of 0 provides a bound on f prime of h. Moreover, you can calculate f of 0 as minus gmm over r squared, and f prime of 0 is 2gm over r cubed, right? And so I can just use Taylor's theorem to find an approximation for the force of gravity just up to linear terms, right? So like f of h will be the constant term, and then plus or minus this gmm over r cubed. I'm not sure I have plus or minus here. Why did I put a plus or minus there? Doesn't seem like there should be a plus or minus there. Well, that's mysterious to me. I think that should just be plus, because when you differentiate, it changes the minus to a plus, right? It should just be plus. I don't think I need a plus or minus there. Anyway, that aside, so what would the error be, right? What would the error be if you just take take gravity and just use this first term as the approximate formula for the gravity force, which is actually variable, right? Gravity is actually inverse square, right? If we use F equals mg, that means we're neglecting higher terms in the Taylor approximation, right? So like in particular, Lagrange's formula of the remainder says the error in using this term and neglecting that term is just about as big as this term, right? That's what Lagrange's formula for the remainder really says. So the error would be something like 2gmm over r cubed times h, where h is the altitude. And if you put in the numerical constants here, you've got about 3.1 times 10 to the minus 6 times your mass times your altitude. Not too shabby, right? So suppose your mass is, I don't know, let's keep it simple. Suppose your mass is 100 kilograms, right? What would your altitude have to be for this to be significant? What is this? What's the size of this? If your mass is 100 kilograms, that's about 100 times 9.8. It's about 10,000 newtons, all right? If your mass is 100 kilograms, well, wait a minute, not 10,000. 9.8 times 100 is what? About 1,000, right? About 1,000 newtons will be your weight if you're 100 kilograms. So if I have 100 kilograms here, right, that basically makes this 3.1 times 10 to the minus 4th. So I have to get to a height of what? It's like 10,000, yeah, like 10,000 meters just to get a newton. Relative to the, what did I say was up here? This was what, 100? About 100, right? So to be a percent off, I'd have to be something like 10,000 meters with my silly example. And so you can see that it's a really good approximation right? This F equals mg if we're close to the surface of the Earth. So let's see here. So I think I divided by g and just come up with some acceleration. So like for example, at 10,000 meter, I calculated the error is about 0.03 meters per second squared. At 100 kilometers, the error is around 0.31 meters per second squared. So you can go up pretty high, and the F equals mg formula is still pretty close to right. You got to get way out there. In terms of manned spacecraft, I mean, I don't think manned aircraft can really experience much of a difference. I mean, even at 60 miles, you only have 0.31 meters per second squared. Acceleration from gravity is like 9.8 meters per second squared, right? So that's relatively small. Maybe it's starting to get around like, what, 3%, 4%, something like that. Anyway, I just wanted to show you that we can actually apply what we're doing to real-world problems to say really quite concrete things, and that's why we're covering this material in part. On the other hand, the effort it took me to put this example together is easily the effort that it would take you to do a quarter of your homework, so I don't really ask you these, do I? Because you've got enough math going on without being besieged with some sort of real-world problem like this, right? Anyway, can I put it away, or do you have any questions? No? All right, let's see if the button works. First of all, I'll get my lights back on. Ha-ha! All right. Excuse me, I must partake in a delicious caramel coffee candy in the interest of not coughing like a fiend. So you guys got questions about your homework? I would be happy to help you with them. I can always show you more examples, but as I think back about my life, I've showed you most of my tricks already in here. I still have a few more to go. Yes, which one? 12.6, number 43, yes. Yeah, so, when I assigned these problems, I thought this problem was more interesting than it is. I mean, honestly, like, I think problems 25 through 32 are more interesting than these, because they actually, numerically work out some kind of estimate. This is just sort of a symbolic problem. So you're supposed to find Lagrange's formula for the remainder. Yeah, f of x is equal to 1 over 1 minus x, right? This one? You're supposed to write Rn of x. And so what's Lagrange's formula for the remainder? It looks like this, right? Fn plus 1 of c divided by n plus 1 factorial x to the n plus 1. So basically, that's all you have to do. You just differentiate n times and plug a c in, and that's it. Now, as I was just saying, I think this is more interesting in some sense when you ask the additional question, like, okay, I want the error to be less than such and such, then, what n do you have to use in order to make it so? But here, I guess the question is, how do you differentiate that n times? Right? One way is just directly differentiate. That's not too bad for this one. What's f prime of x? So there's 1 minus 1 from the chain rule, right? There's another minus 1 because it's the reciprocal function. So you get, right? Then you differentiate again. You get minus 2 times minus 1, right? Let me just clean it up a little bit before I go to the next step. This is 2 divided by 1 minus x cubed. I mean, this is an odd problem. I don't mind working it out for you. You already know the answer, right? What's the third derivative? 2 times minus 3. The thing about the differentiation here is there's always the minus power that you're differentiating from, like the just plain old power rule. Excuse me. And then there's the following minus by the chain rule, because the inside function is 1 minus x, and those always compensate to give you a plus, and that's the pattern here, right? So I think if you have a little bit of imagination, you can already see the formula here. This is 3 factorial, and so forth. I mean, if you just tilt your head and squint, you can see that the nth derivative at x is equal to, well, it looks to me like n factorial, yeah? Yep, divided by what? 1 minus x to the what power? N plus 1, yeah. So, thus, Rn of x is what? Rn of x is going to look like n factorial divided by 1 minus c, parentheses to the n plus 1, right? That's just sorry, as I was working out these homework problems, because, unfortunately I don't have time to do all of your homework problems in advance. I mean, I try to take a look at them and figure out what they are before I assign them. But I thought this was more interesting than it actually is. Anyway, that's this, right? And then what? So you still got your 1 over n plus 1 factorial, and you still got your x to the n plus 1. So you can do some simplification there. So what's n factorial over n plus 1 factorial? Yeah, 1 over n plus 1. And then I can write x over 1 minus c to the n plus 1 if I want. There you go. That's probably the answer in the back of the book. I don't know. Is it?
In the back of the book, it had 1 over 1 minus c plus 2 times x plus 1.
Oh, very good. I made a mistake. You guys tell me how.
Like the 1 minus x cubed, that'd be 1 minus x to the 4th.
That's not the mistake. The mistake is what's encircled in red. I haven't done what I've advertised to do. If that's the nth derivative, I don't need to look at the nth derivative, right? I need to look at the n plus first derivative, right? Which would be n plus 1 factorial divided by 1 minus x to the n plus 2, right? And then I plug in c. So I should have n plus 1 factorial and then 1 over n plus 2 like that, right? And then you see what happens. These guys just straight up cancel. And so we get what you just told me from the back of the book, which is 1 over quantity 1 minus c to the n plus 2 power, and then x to the n plus 1. And again, I mean, Lagrange's theorem actually says there exists a value c that you can plug in there that'll make this precise, right? But this problem doesn't ask you to find that either, does it? I'd like to take a more interesting view of this, number 43. Something I should tell you guys about. Check this out. A standard example. If you have 1 plus u to the, let's say, k power this is equal to 1 plus ku plus 1/2 k times k minus 1 u squared plus 1 over 3 factorial k times k minus 1 times k minus 2 u cubed plus 1 over 4 factorial k times k minus 1 times k minus 2 times k minus 3 u to the fourth, and so forth. This is the so-called binomial series. If you go looking for this, you'll see it in the homework, a lot of different places. This example even, you can look at it in this way, right? So like 1 plus u to the minus 1 power is what? Or x, rather. Well, fine. 1 plus u. Yeah. Excuse me. 1 minus u, right? Plus 1/2 minus 1 times minus 2 u squared 1 over 3 factorial minus 1 times minus 2 times minus 3 u cubed, and so forth. You see what's happening here? That's a 2 factorial, that's a 3 factorial. If I went to the next, I have a 4 factorial, right? And it all collapses down to just what? Of course, this is totally unsurprising, right? Because this is also equal to 1 over 1 minus a minus u, right? AKA a geometric series with ratio minus u. Now, if you plug in u equals to minus x, what do you get? So this is an overlapping case. This case, the binomial series and the geometric series. This is where they're both applicable. It's not usually the case. Did you guys, if you think about it, there's another homework problem where you can see this pattern coming up. You calculated the like the 6th Taylor polynomial or something for which one was it? I noticed that. Did I have you do number, was it number 5 and 12.6, or what was it? Oh, anyway, I just wanted to make you know, I wanted you to be aware that this binomial series is an important example. It's been with us since the very beginning of calculus. It's something Newton knew. It's part of what allowed him to be sure about the validity of his new infinitesimal calculus. It's more formally discussed on page like 634, and I've included a problem about it in your last homework in chapter 12, right? I don't know if you're there yet or not, but you will be eventually. Excuse me. It's just this is on the same footing as like sine or cosine or exponential. It's one of or geometric. It's something you should know in terms of just your general calculus knowledge. It's healthy to know this. It's most often used in applications to science in the following way. That's usually how it's used. In particular, the most common application I saw of it as an undergraduate, something like this. If x is small, 1 over 1 plus x is equal to 1 minus x. That's usually how it's applied. At least in the applications I'm familiar with in physics, that's usually what happens. And if you don't know about, because k is minus 1, if you don't know about the binomial series, this is, from an algebra perspective, this is dark magic. I mean, what on earth is that? That's not cool. Like, and of course, the places you'll have it applied, no one writes the approximate. It's like equals. It'll drive you nuts. You're like, that's not equal. What? Well, they're using binomial series. Okay, you guys have other questions? Let me shut up. 58? Did I hear that right?
Yeah.
12 point what? Did I sign that? Oh, that's like the problem beyond the problem I've solved at the moment. Aha. The series we derived for the natural log 1 plus x converges too slowly to be of much practical use. The following series expansion is much more effective. Okay. Oh, come on. Where did I put my... Oh, there it is. Oh, I hope you guys see the binomial series is pretty easy to derive. Like, I don't think I need to go through the derivation with you because I've done that example. I mean, if you do any one of these examples, these kinds of examples, and you just see the pattern that comes up in the Taylor series, you'll understand immediately where the binomial series formula is coming from, right? It's just when you repeatedly differentiate a power function, you get products of the power, and then 1 less the power, and then 2 less the power, and then 3 less the power. And if you're looking at n-fold if you're looking for a repeated differentiation, that's where those binomial coefficients are going to come from. I probably should talk about that more some other day, but let me focus on your homework here. Natural log 1 plus x over 1 minus x. We're supposed to show this, right? Is equal to, what is it? 2 times, let's see here, x plus x cubed over 5 plus x to the 5th over. Wow, this is snazzy. Oh, 3. I was like, why is it all 5s all the time? That's weird. No, it's just wrong. Okay. If there's anything we've learned in the last few years as a society is that weird is never wrong. Weird is the new normal. Let's see here. 1 plus x. Come here for here. Oh, we're supposed to derive this, eh? Interesting. Well, first of all, let it be understood that you do not have to do 12.6 homeworks with 12.6 technology. If you want to do 12.6 homework in using the techniques I've shown you in class, you're free to do that. Now, if you've already done it with the, low tech, let's say just repeated differentiation approach, that's fine. Nothing against that. But I would like you to understand, for example, something like problem, where was that thing? Where is that thing? Man, I can't find it. Maybe it's in 12.7 I'm thinking of. Somewhere there's a problem like cosine of x squared times x. Is that in here? So like x times cosine x squared. Probably by now most of you have done it, so I'm not telling you anything you haven't already done. But suppose you haven't. This is the way you should do this. See, because we're just letting u equals x squared and looking at the expansion of cosine of u, which is 1 minus 1 half u squared plus 1 over 4 factorial u to the 4th, right? And so if you want to calculate this to 5th order, just peel off the 5th order terms. So this is my solution, all right? And I'm sharing it with you because I also want you to understand this way of thinking. If you have known Maclaurin series, you can peel off Taylor approximates that you want by just truncating the series. And golly, it's a lot easier to plug in x squared into the cosine series, multiply by x, as opposed to actually differentiating that thing 5 times, right? Those of you who've actually already done this problem agree with me, yes? Okay. Well, I'm sorry, did I already talk about this? Okay, I'm stalling. How do I do this one? Any ideas, guys? I like that. So we're going to let f of x equal to the log of 1 plus x minus the log of 1 minus x. I like that a lot. My next move would be to differentiate this thing. And here's where I'm probably going to divert with what you might have done. If you're in the spirit of 12.6, you're just going to repeatedly differentiate and use the what? The Taylor formula, right? I'm not going to do that. I'm going to do it 12.9 style. So check it out. Yeah, thank you. Right? Now this is a sum of geometric series. This is the sum, k equals 0 to infinity, of minus x to the k plus the sum k equals 0 to infinity of x to the k. By geometric with r equal to minus x, and with geometric with r equals to x. Now, if you look at this we can simplify, right? Because what you got is you got the sum k equals 0 to infinity of like minus 1 to the k, right? Plus 1, parentheses, x to the k. See, I've got a common power here once I use the fact. Do you see what I did there? Agree? And then you have matching apples and apples, we can add them, right? These kinds of series we can add. This mysterious coefficient, minus 1 to the k plus 1, what does that actually do? Can you simplify that? You should simplify that. Yeah. Well, this right here, see, this is actually equal to minus 1 parentheses times x, right? So then if I raise that to the k power, that's equal to minus 1 to the k times x to the k, right? So this term gives me that. And there's a, if you use your imagination, you can see there's a 1 over here. Excuse me. And that's this one. Okay. You're right, one more step. I'm not sure where you're coming from there. So the next step would be sum k equals 0 to infinity. So you agree with this step, right? But then I have matching powers, so I can just add coefficients. That make sense? Or? Okay. So, what is that? So if you look at this, this is 0 when k is what? Odd, right? So this, we can rewrite this as the sum j equals 0 to infinity of, now I agree with you, 2 times x to the 2j, because the odd terms are 0. And in the even case, you know, minus 1 to the 2j plus 1 is just equal to 1 plus 1, which is equal to 2. So in the case that they don't cancel, you just get a 2 there. Now what? I'm out of time, but to complete the thought, then you just integrate to undo the differentiation we did, right? And if you integrate this series, right, take this and integrate, you'll get that series. And then, of course, you have to add a constant and make sure your constant's the right thing. Your constant works out to be 0 again. Eventually, I'm going to find an example where you have to set that constant to something other than 0. You'll see. Anyway, for those of you, are there any other particular questions you guys have? If you have a particular thing that's bothering you, I can make a point to try to work it in the second section. Any requests? Number 12.8, number 14? Yay. Alrighty. Well, guys, I will see you tomorrow. 34C of which section?